Imagine a high-speed train, packed with passengers, just hurtling down the tracks at incredible speeds. Or maybe think about a complex city subway system moving millions of people every single day seamlessly and safely. Have you ever stopped to think about the invisible force making all of that possible? Is this incredibly sophisticated symphony of software running silently in the background, making split-second decisions and ensuring, well, flawless operation, but how do we know? How do we really know that software is truly safe, especially when actual lives are on the line? In this domain, the expectation isn't just high, it's absolute. We expect perfection, right? The extraordinary safety record of railways isn't an accident. It's the result of meticulous, painstaking engineering. And the digital brain behind these systems of software, it isn't just some nice enhancement. It's really the beating heart of safety itself. Its reliability is absolutely paramount. So today, we're pulling back the curtain on how this incredibly critical railway software is developed and verified and certified to be safe. We're going to explore the rigorous, multifaceted techniques engineers use. Everything from foundational testing strategies to advanced mathematical formal methods and even cutting-edge model-based development. It's all designed to ensure every single line of code is trustworthy. And this isn't just theory, it's about practical, real-world engineering and its direct life-saving impact.
Yeah, and what's fascinating here is how the railway landscape itself has dramatically evolved. That adds whole new layers of complexity to these safety considerations. We've moved towards more liberalized services. We've seen the separation of the physical infrastructure from the day-to-day operation. And there's this relentless global push for high-speed networks and, crucially, European interoperability, allowing trains to cross borders seamlessly. Every single one of these shifts fundamentally impacts how we think about safety. And this evolution is driven by technology. Modern railway systems increasingly rely on innovative signaling equipment, like the European Rail Traffic Management System, ERTMS, and its train control component, ETCS. We also have advanced monitoring systems, like onboard diagnostics, wayside sensors. These devices are just teeming with complex software. And that software often accounts for the major part of their design and development costs. And this software is incredibly flexible, which is fantastic for innovation, right? It allows for incredible new solutions and efficiencies. However, that very flexibility also notoriously introduces the risk of what we commonly call bugs, software faults. So if we connect this to the bigger picture, the fundamental challenge for engineers, for operators, and really for all of us is this. How can the exceptionally high safety standards we've come to expect in railway operation be compatible with the inherent threats posed by potential software faults? Today, we're going to explore the answers to that vital question. The foundation of trust. Standards and core principles.
Okay, let's unpack this. When we talk about engineering software for something as critical as a train, it's not just about writing robust code, is it? It's about adhering to a very specific, very stringent rulebook. It's about demonstrating beyond a shadow of a doubt that your software is safe and reliable. In these safety-critical domains like railways, software development isn't just a process, it's subject to a rigorous certification. This process aims to verify that products are developed in conformity with specific software safety guidelines and, domain-specific documents issued by national or international institutions. And the creation of these guidelines, by the way, is a very long and incredibly complex process. It requires mediation, constant negotiation between different stakeholders with often contrasting interests. On one side, you have the manufacturers. They're interested in keeping development costs low, naturally, but they also have to pay immense attention to the safety of their products. I mean, a single accident due to product failure could mean losing clients, not to mention the unimaginable human costs.
Absolutely. The stakes are incredibly high for them.
Then you have the certification bodies. Their sole responsibility is to certify that a product is safe with a reasonably high certainty, according to the running laws and norms. They tend to give less priority to production costs, focusing purely on that safety aspect.
Right. Their mandate is safety assurance above all else.
And finally, you have the clients, often the railway operators themselves, who provide services to the final users. They're interested in balancing cost containment with the paramount need for safety assurance for millions of passengers. Due to these contrasting interests, the actual production of these guidelines is a slow process, full of necessary trade-offs and compromises. Typically, a new edition of guidelines takes about a decade to be issued. Yeah, a decade. Once they are issued, they become the absolute reference standard for that particular domain until the next edition comes along. And this is also a reason why the railway signaling sector has historically been a bit slower, perhaps, to adopt technological innovation compared to other domains, especially for functions that have a significant impact on safety.
That makes sense. Change requires consensus. And consensus takes time when safety is non-negotiable. To truly grasp this, it's vital we understand a key difference in how safety is officially recognized. The distinction between two critical types of certification. You have process certification and product certification. Process certification is designed to guarantee that the production process itself has followed all the established guidelines and norms. It's about ensuring that the factory, the methodology, the entire workflow can consistently deliver products of an expected quality level. Think of it like auditing a manufacturing plant's entire operational workflow to ensure every step from raw material to assembly line adheres to the highest quality control. On the other hand, a product certification aims to guarantee that a specific individual product has been designed and developed according to determined quality guidelines. This is more like inspecting a finished car before it leaves the lot, ensuring that specific car meets all safety standards and design specifications. For safety certification in railways, there's a heavy emphasis on product certification. Makes sense, right? You need to know this piece of equipment is safe. But it also universally demands that the development process itself complies with certain quality and maturity standards. It's not enough for the car to be safe. The factory making it must also be safe and adhere to stringent safety protocols. Now, for railway systems, the key standards often come from CENELEC, the Comité Européen de Normalisation Électrotechnique. This includes standards like EN 50126, EN 50128, and EN 50129. While they share commonalities with the general IEC 61508 standard for embedded systems, they uniquely reflect the peculiar railway safety culture, which has a history stretching back more than a century. Briefly, EN 50126 defines concepts like reliability, availability, maintainability, and safety ramps, as it's often called. EN 50129 gives guidelines for hardware safety design. And crucially for our discussion today, EN 50128 provides the guidelines for software production. Now, EN 50128 was initially issued for railway signaling systems, but its use has really spread to a full range of railway applications, though new specific standards are emerging too, for example, for software onboard rolling stock. When it comes to the actual software development cycle, EN 50128 doesn't mandate one specific method. It's not prescriptive in that way. Instead, it describes generic phases the process should follow and the attached documentation required. One of the most common and widely recognized examples of a suitable software lifecycle is the V model. You can visualize it as a V shape. The left branch represents the design cases, starting with requirement analysis, moving to architectural design, then detail design, and finally coding. The right branch represents the corresponding verification phases: unit testing, integration testing, system testing, and ultimately maintenance.
And those dotted arrows you mentioned.
Right. The dotted arrows you might imagine between the two sides show the direct relationship. They link the tests carried out on the right branch back to the artifacts produced in each phase of the left branch. So testing requirements comes from the analysis phase, testing architecture from the design phase, and so on. This V model vividly illustrates the intense focus on verification and testing activities, which is so typical of safety guidelines. It graphically shows that verification and testing costs are actually comparable to the costs of design and development. It's a huge chunk of the effort. And critically, these verification activities need to be planned and prepared for during the design phases, not just tacked on at the end. Interestingly, EN 50128 itself provides very little guidance on technical choices, like, say, how to develop a suitable software architecture. Instead, it's much more concerned with the impact different software engineering techniques can have on the safety of the final software. And it also explicitly requires that verification and testing activities are carried out independently. It accurately defines different roles for these activities, depending on the software component's safety integrity level, or SIL.
SIL. Okay, so here's where the importance, the criticality of each piece of software is officially weighed. We're talking about the safety integrity level. The software SIL is defined as an attribute of a software component that indicates its required robustness, specifically regarding protection against software faults. It has a value between 0 and 4. And the higher the SIL, the higher the assurance required that the software is free from faults. So it's like a spectrum of criticality. The SIL is assigned to components through a system safety assessment process. It's based on the potential impact on safety if that component were to fail. So a component with no effect on safety would be SILU. A highly safety-critical component where failure could have catastrophic consequences would be SIL4, and this assignment, it has profound implications. It dictates that specific development and verification techniques deemed suitable for that level must be used. EN 50128 lists these techniques in tables, categorized by the strength of their suggestion. For example, M means mandatory, it must be used, no exceptions. HR means highly recommended, it should be used, and if you don't, you need to provide a formal justification explaining why not. R is recommended, and then there are others like no indication or not recommended. The standard puts special emphasis on safety-relevant errors, as you'd expect. It's also worth noting that beyond software SILs, EN 50128 also classifies the tools used in software development. This includes testing tools and formal verification tools. Tools of Class T1 don't directly contribute to the executable code. Think maybe like project management software. Class T2 tools support testing or verification. Errors in these tools could hide defects, but wouldn't directly cause errors in the executable software itself. So a test coverage tool might be T2. And Class T3 tools are those that directly or indirectly generate outputs contributing to the executable code itself, like code generators. These have the strictest requirements. For each class, the norm lists specific evidence that must be provided about the tool's actual role and its validation. This ensures that even the tools used to create and check the software are themselves trustworthy. It's layers upon layers of assurance.
Exactly. Trust in the process, trust in the product, and trust in the tools used to build and verify it. 2. The systematic search for faults. Software testing.
So, with those stringent rules in mind, how do engineers actually hunt down potential faults in the code? Their primary weapon, and indeed a massive undertaking, is rigorous software testing. It's not just about asking, does it work, but more like, can we break it, and if it breaks, does it fail safely? Testing activities really consist of the systematic search for faults in the software. In the railway safety critical domain, testing isn't just fundamental, its cost, as you said, is often comparable to the cost of the actual software coding itself. It's a huge part of the budget and schedule.
Yeah, absolutely. So to lay the groundwork for a dive into testing, let's quickly define some key terms, just so we're all on the same page. Imagine a program as a function. It takes input data, let's call the set of all possible inputs D, and produces results, R. The correctness of a program, let's call it OKPD, is basically a true-false statement. Does program P produce the expected value for a given input D? A test, or test suite, or test set T, is simply a specific subset of all those possible input data in D. And each individual input within that subset T is a test case, T. A test is considered passed if it doesn't reveal any faults, meaning the program is correct for all the test cases T in that set T. It fails otherwise. Simple enough.
Okay, test case, pass, fail.
Got it. Now, a selection criterion, C, is a set of rules or predicates that guide which inputs are chosen for a test. It helps us pick the right T's for our T. For test T to be selected by a criterion C, 2 conditions must hold. First, every test case T you pick must satisfy at least one of the predicates in C. And second, each predicate in C must select at least one test case T in T. It ensures the criterion is fully covered by the test set. Now, a truly exhaustive test would involve testing all possible input values. T would equal D. If such a test passed, it would imply the program is correct for all inputs. That would be ideal. However, for complex software, it's usually completely impossible to exhaustively test a program. The number of inputs is just too vast, often infinite. And this brings us to a crucial point, a fundamental limitation of testing. Testing can reveal the presence of faults, but it cannot definitively prove their absence.
Right. You only know it works for the inputs you tested. You can't be sure about the ones you didn't test.
Exactly. It can tell you what is wrong, but not guarantee what isn't wrong. And importantly, all these definitions assume that for each test case, the requirements clearly tell us the expected outcome, which links directly back to those horizontal arrows in the V model we discussed earlier.
Okay, so the V model really stresses planning that verification from the start. And that often begins at the smallest level, right? Like diving into the individual components of the software with unit testing. Unit testing aims to verify whether a single code unit, maybe a function, a module, or a class, is correct with respect to its expected behavior. And depending on how we choose those test cases, we distinguish among functional testing, structural testing, and statistical testing. Let's break those down.
Let's start with functional testing. This is also known as black box testing or requirement-based testing. The key here is that this approach is performed purely on the basis of the functional requirements, what the unit is supposed to do without ever looking at its internal code structure. It's like testing a black box. You only care about what goes in and what comes out. The internal workings are irrelevant for this type of test. For functional testing, there are common criteria for selecting tests. One is equivalence class partitioning, or ECPT. Here, the input domain of the unit is divided into equivalence classes. The hypothesis, or assumption, is that one test case from each class represents all the values for that same class. For example, if you have a system that accepts ages between 18 and 65, you might define classes like below 18, 18, 65, and above 65. Then you test one value from each class, say 10, 30, and 70.
Assuming if 30 works, then 40 and 50 should also work because they're in the same valid class.
Precisely. Closely related and often used together with ECPT is boundary value analysis, or BVAN. With this, test cases are specifically chosen at the boundaries of those equivalence classes. So for that 1865 range, you'd test 17, 18 the lower boundary, 65 the upper boundary, and 66. This is incredibly effective for catching typical programming errors, like off by one errors, or where a programmer might accidentally use a less than condition instead of less than or equal to. Those boundary conditions are notorious error hotspots.
Yeah, I can see that, like testing right at the edge cases.
Exactly. The edges are where things often break. And finally, there's test case by error guessing. This is less formal, but still valuable. This is where domain experts, leveraging their intuition and extensive experience with the code and the application domain, select test cases to probe for common or likely errors they anticipate based on past experience.
So kind of relying on expert intuition.
Yeah, it harnesses that deep knowledge. It can be surprisingly effective at finding tricky bugs. Okay, moving from external behavior to internal structure, we have structural testing, sometimes called white box testing. Here, the selection criterion for tests is derived directly from the structure of the code unit, particularly its control flow graph, how the code branches and loops. The goal is to ensure that the selected tests exercise or run through all the various structures within the program. We use a coverage measure to indicate if all these structures have been exercised. This measure is simply a ratio, the number of executed structures divided by the total number of structures in that category. The aim, ideally, is 100% coverage for the chosen criterion. Let's break down some specific coverage criteria, starting simple and getting more complex. Statement coverage is the most basic. It ensures that tests cover every executable line of code at least once. It's like making sure you've walked down every corridor in a building at least once. If your coverage value is 100%, it means every single statement has been executed by at least one test case.
Okay, simple enough. Every line gets run.
Then there's branch coverage, also known as decision coverage. This is stronger. It requires that all branches of the program's control flow graph are executed. That means at every conditional statement, like an if-else or a loop condition, both the true outcome and the false outcome must be taken by at least one test case.
So if there's an if statement, you need a test that makes it true and another that makes it false.
Exactly. It's like at every fork in the road, you ensure you take both paths at least once during your testing. Basic condition coverage takes it a step further. It requires that all individual Boolean conditions within complex conditional statements are exercised for both true and false outcomes. So if you have an if A and a B statement, basic condition coverage needs tests where A is true, A is false, B is true, and B is false. However, this doesn't actually guarantee 100% branch coverage. Why? Because some combinations of these basic conditions might not be exercised, and thus some branches, the overall true-false outcome of A and a B, might not be executed. It's a subtle difference. Now, on the really intensive side, you have compound condition coverage. This requires that all possible combinations of Boolean values obtained from the basic conditions within a decision are exercised at least once. For that if A and a B example, you'd need tests for A true, B false, A false, B true, and A false, B false. This can quickly lead to an exponential number of test cases, 2 to the power of n, where n is the number of basic conditions.
Whoa, okay. So if you have like 10 conditions, that's over 1,000 test cases just for that one if statement.
Potentially, yes. It means as cost grows exponentially, making it often completely impractical for complex systems with many conditions.
So that compound condition coverage sounds thorough, but maybe overkill or just too expensive. Is there a better balance?
There is. And this is where modified condition decision coverage, or MCDC, becomes incredibly important, especially in safety-critical systems like aerospace and railways. MCDC is clever. It considers the Boolean values obtained from basic conditions in relation to their larger Boolean expressions. It ensures that each individual condition is shown to independently affect the outcome of the overall decision. The key thing is MCDC implies branch coverage, so it's strong, but its cost typically grows linearly with the number of conditions, not exponentially like compound coverage.
Oh, okay. So it's a much more efficient way to get strong assurance.
Exactly. It hits a sweet spot. It requires, roughly, n+1 test cases where n is the number of conditions. That's much more manageable. For instance, if you have a complex if statement like if x0, y gives a y2, 2, MCDC defines specific combinations of true-false for each part, x0, y, dag at a c, etc., that must be tested to show each one matters independently. It's a highly efficient and powerful criterion, which is why it's often mandated or highly recommended for high ILL levels. And finally, the strongest criterion is path coverage. This requires that all possible execution paths through the program's control flow graph are exercised by the test set. This is the most challenging. Why? Because the total number of paths can grow exponentially with the number of decisions, and it becomes technically unbounded if there are cycles or loops in the code.
Loops seem like they'd make it infinite, right?
They do, theoretically. So for cycles, we often use a practical approach called K coverage, meaning you test a finite number of iterations, typically K1, which means testing the path where the loop is skipped, 0 iterations, and the path where it executes once. Another challenge is unfeasible paths through the code that cannot possibly be exercised by any input data. These are actually quite common in railway safety critical systems due to defensive programming, where code is written to cope with potential hardware or software failures, sometimes creating additions that can't logically occur together in normal operation. So in evaluating path coverage, it's often limited to feasible paths. The unfeasible ones usually need to be justified and verified through meticulous code inspection or analysis. So you see this hierarchy, right? Statement coverage is the weakest and least expensive, then branch, then MCDC, then path coverage is the strongest and most expensive. Choosing the right level depends on the criticality, the SIL, and the trade-off between assurance and cost. Now, briefly, there's also statistical testing, in contrast to functional and structural tests, where test data are provided by a deterministic criterion like boundaries or paths. Statistical testing uses random, or more accurately, pseudorandom test data. These are often generated according to an expected distribution of the input data the program will see in the real world. In practice, this often means combining statistical tests with others. You might first apply a functional test, then maybe a statistical test, and then measure the resulting structural coverage. If that coverage isn't sufficient according to the standard for that SIL level, then new targeted structural tests are defined to increase it. Okay, so to practically perform all these unit tests, you need a few key components in your toolkit. First, you need a driver. This is basically a small program or script whose sole purpose is to invoke the unit under test, passing it the specific test cases you've defined. Second, you often need stubs. A stub is a dummy module that mimics the interface and behavior of any other modules that are invoked by the unit you're currently testing.
Ah, the stand-in actors again.
Exactly. They allow your unit to perform its part without needing the entire complex system to be present. They provide canned responses or simple logic just sufficient for the unit under test to run. Third, you need an oracle. This is the entity. It could be another program, a script, or even a human user that decides whether the test passed or failed. It compares the actual output of the unit under test with the expected outcome defined by the requirements. It's the judge of the test. And finally, especially for structural testing, you need code instrumentation. This involves including special instructions within the code itself automatically, usually that allow you to observe the test execution and measure things like which statements or branches were executed. This is how you calculate those coverage measures.
Okay, that makes sense for testing the individual pieces. But once those units seem okay in isolation, the next critical step is making sure they actually work together correctly. That's integration testing, right? After the coding phase and adequate unit testing, it's essential to perform integration tests to verify the correctness of the overall program, specifically looking for issues caused by incorrect interactions between the different modules. You mentioned there are a couple of main ways to approach this. The first sounds a bit risky, the non-incremental approach, sometimes called the Big Bang test. This involves assembling all the previously tested modules at once and then performing an overall analysis of the entire system. It seems simple in concept, maybe faster up front, but if you find an issue, how do you know where it came from? It sounds like finding a needle in a haystack.
That's exactly the problem. It's simple to set up, perhaps, but debugging can be a nightmare because it's very difficult to pinpoint where the interface anomaly occurred among all those interconnected modules.
So the alternative is the incremental approach. This sounds more methodical. It consists of testing individual modules and then gradually connecting them to their caller or called modules, testing their composition as you go, step by step, until the whole system is complete.
Right. This method offers several advantages. You don't need all modules to be fully tested up front. And crucially, it makes it much easier to locate interface anomalies because you're adding and testing pieces in smaller chunks. When something breaks, you have a much better idea of where the problem lies, likely in the connection you just made. It also allows for multiple exercises of the modules as they get integrated into larger assemblies.
And within that incremental approach, there are strategies.
Yes, typically top-down or bottom-up. Top-down starts from the main module and gradually integrates the modules it calls, often using stubs for the lower-level ones initially. Bottom-up begins by integrating the basic low-level functional units first, testing them together, and then building upwards towards the main unit, often using drivers to simulate the higher levels.
And how do you measure progress here? Is there an equivalent to code coverage?
A common criterion used for integration testing is procedure call coverage, which indicates how many of the interfaces or procedure calls between modules were actually exercised by the integration test suite. Okay, so once integration testing has thoroughly exercised all the functionality of the entire system, making sure the pieces work together, we're still not done. It's still necessary to test certain global properties that aren't strictly related to individual system features, but to the system as a whole. This is the role of system testing. System testing typically includes several crucial types. A stress test or overload test checks that the system complies with specifications and behaves correctly even under extreme conditions, for example, when there's a maximum number of users logged in, or the maximum number of simultaneous connections with other systems, pushing it to its limits. A stability test checks the correct behavior of the system over prolonged periods of continuous use. For instance, if dynamic memory allocation is used, this test ensures that things like memory leaks don't cause Stack Overflow errors after, say, days or weeks of operation. You need to know it can run reliably for a long time.
Right, like leaving it running for a weekend or longer just to see if anything weird happens.
Exactly. Then there's the robustness test. Here, the system is intentionally provided with unexpected or incorrect input data to check its response. Does it handle garbage gracefully, or does it fall over? A typical example might be using a tool to send random input to a user interface to see if it shows anomalous behavior or crashes.
Trying to actively break it with bad data?
Pretty much. Then there's compatibility testing. This verifies the correct software behavior when connected to the specific hardware devices it's designed to work, with sensors, actuators, network interfaces, etc. And interoperability testing is hugely important for modern railway systems, especially with things like ERTMS. It verifies the correct behavior when connected with other systems of similar nature, particularly those provided by different vendors, ensuring they all follow the established communication protocols and understand each other. And finally, and absolutely critically for railway safety, is the safety test. This verifies the correct behavior of the system, specifically in the presence of violations of its safety conditions. For example, it checks that when a safety violation occurs, like conflicting signals or a sensor failure, the system correctly detects it and transitions to a predefined fail-safe mode, ensuring that any malfunction prioritizes passenger safety above all else.
So simulating failures to make sure the safety mechanisms kick in properly.
Precisely. To perform these system tests, especially for complex railway control systems, specialized instruments are often required. This includes ad hoc hardware simulators and sophisticated software simulation tools employed to accurately recreate the exact environment, the inputs, the timing, the other systems in which the software will actually be executed in the real world.
Now, software rarely stays static. Updates happen, bugs get fixed, new features are added. When a new version of a product is released, the biggest fear is accidentally breaking something that used to work or introducing new flaws. This is where regression testing comes in, right? Its purpose is to repeat previous tests to check whether changes to the product have inadvertently introduced new faults or reactivated old ones that were previously fixed. The goal here is efficiency, minimizing the cost and effort by reusing existing drivers, stubs, oracles, and repeating relevant test cases from prior versions. But you can't just rerun all the old tests every time, can you? That would take forever.
No, exactly. That's why, before performing regression testing, an impact analysis is explicitly required by standards like EN 50128. You need to analyze the changes made. Which modules were modified? How might that affect other parts of the system? Even a seemingly small change can potentially impact structural test coverage significantly elsewhere in the code. This analysis helps identify which tests need to be rerun, and sometimes it necessitates defining entirely new test cases to bring the coverage back up to the required values for the affected areas.
So it's a targeted retesting based on what changed.
Yes, but with a crucial caveat. For safety-critical railway systems, the standard is extremely strict. At least the safety tests have to be repeated completely, even after minor changes. You simply cannot compromise on verifying those core safety functions after any modification. This rigorous re-verification is absolutely non-negotiable because the potential consequences of a regression fault are just too severe. And one more testing technique worth mentioning is mutation testing. This addresses a fundamental question. How do we know our tests are actually good at finding errors? Mutation testing helps evaluate the ability and the effectiveness of the tests you've performed. How does it work? Well, faults are intentionally introduced into the code. These are called mutations. They're typically small syntactic changes, like changing a plus-and or a plus-and or a plinnet. The idea is that an ideal test suite should be capable of killing these mutants, meaning at least one test case should fail when run on the mutated code, thus revealing the injected fault. If your existing tests don't reveal these deliberately introduced faults, if the mutants survive, it indicates that your tests themselves might be inadequate for catching certain types of errors, and more sophisticated or targeted tests need to be defined.
So you're basically testing your tests by seeing if they can catch deliberate mistakes.
Precisely. It's a way to measure the quality and fault-finding capability of your test suite. This intentional introduction of faults is also used sometimes to evaluate the robustness and safety of the software under fault conditions. And in that context, it's often referred to as fault injection or fault-based testing.
Okay, so tying this all back to the core standards we started with, EN 50128 isn't just a suggestion book. It specifies precisely what's required for testing, especially depending on that SIL level. For functional or black box testing, it's considered mandatory for software components at SIL 3 and SIL 4, the highest levels, and it's highly recommended for SIL 0 through SIL 2. Specifically, techniques like equivalence class partitioning, ECPT, and boundary value analysis, BVN, are highly recommended from SIL 1 all the way up to SIL 4. They see those as fundamental.
Yes, they're considered essential good practice across the board.
And when it comes to structural coverage, statement coverage is highly recommended from SIL 1 to SIL 4. So making sure every line is executed is a basic expectation. But for the higher levels, SIL 3 and to SIL 4, the finer coverage measures, such as branch coverage and especially that efficient MCDC, are additionally highly recommended.
That's right. The higher the safety integrity level, the more stringent, the more rigorous, and the more detailed the testing requirements become. The standard essentially forces a level of diligence appropriate to the potential risk. 3. The precision of formal methods, proving correctness.
Okay, so testing is clearly a massive, crucial part of the process. It's like this highly sophisticated bug hunting expedition, constantly searching for flaws. But then there's another whole category of techniques, formal methods. These sound, well, more mathematical. Are they about building the software in such a way that the bugs simply can't exist in the first place? Or even proving their absence?
That's a good way to put it. While testing finds bugs, formal methods aim to prevent them or mathematically prove they aren't there. Now, you're right to mention proving absence. Generally, proving the absolute absence of all possible bugs in any complex software is considered an undecidable problem in computer science theory. You can't build a perfect universal bug detector. However, formal arguments can, in many specific and critical cases, be used to rigorously demonstrate the absence of certain classes of faults, or to prove that the software adheres to specific critical properties. Today, the necessity of formal methods as an essential step in the design process of industrial safety critical systems is really widely recognized. They offer a level of assurance that testing alone often cannot provide.
So what exactly are formal methods? How would you define them?
In its most general definition, the term formal methods encompasses a range of notations that have a precise, unambiguous mathematical semantics. Think languages based on logic or set theory. And crucially, these notations are coupled with associated analysis and development methods. Their aim is to describe and reason about the behavior and functionality of the system in a formal mathematical manner, leaving no room for ambiguity or misinterpretation. The ultimate goal is to produce an implementation that is provably free from certain defects with respect to its specification. Now, it's important to acknowledge up front that applying these mathematical methods to software development verification is incredibly labor-intensive and, therefore, usually expensive. Because of this, it's often not feasible or cost-effective to formally verify every single property of an entire complex computer program in exhaustive detail. So you don't necessarily apply them to the whole system.
Typically not. The common strategy is to first determine what the truly crucial safety-critical components of the software are. These parts can then be isolated, studied in detail by creating precise mathematical models of just those sections, and then engineers can focus their effort on rigorously verifying those critical models. To achieve this, several different notations and techniques have been developed over the years. First, there's the concept of formal specification. The languages used for this are characterized by their ability to describe the internal state of the target system and precisely define how its operations modify that state. Their underlying foundations are usually in discrete mathematics, set theory, category theory, and various forms of logic. A prominent example you might hear about is the B method, or just B. This method targets the entire software development lifecycle, starting from an initial abstract specification, then moving through multiple verifiable refinement steps, all the way down potentially to implementation and even automatic code generation. Crucially,
Formal verification is applied at each refinement step. This generates what are called proof obligations. These are mathematical theorems that need to be formally proven correct to ensure that the refinement step preserved the properties of the specification.
So you're proving correctness at every stage of detail.
Essentially, yes. The B method comes with its own ecosystem of support tools, including tools for automatically deriving these proof obligations, automated or interactive theorem provers to help discharge them, and even code generation tools in some cases. Then we have approaches based on automata-based modeling. This includes things like state charts, Petri nets, and timed automata. Here, the focus shifts from specifying state transformations to modeling the concurrent behavior of the system, especially how it reacts to stimuli or events over time. A state in the resulting transition system represents a particular configuration or mode of the modeled system. Formalisms like state charts, which are hierarchical state machines, are particularly well suited for specifying reactive, concurrent, or communicating systems and protocols. They're great for visualizing and analyzing complex interactions and sequences of operations.
You mentioned timed automata there again. Could you elaborate a bit more on how the time aspect works in these models? It sounds critical for control systems.
Yes, absolutely critical. Standard automata or state charts deal with sequences of events, but not necessarily when they happen. Timed automata extend this framework to explicitly incorporate the physical concept of time or duration. They do this by adding clock variables. These are special variables that continuously increase at a uniform rate, like stopwatches associated with the system's state. Then transitions between states can have guards involving these clocks. For example, only transition if clock X is greater than 5 time units, and actions that reset clocks.
So you can express things like wait for 2 seconds, then do this, or if this signal arrives within 100 milliseconds, then react differently.
Exactly. It allows for precise modeling of real-time constraints, deadlines, and durations, which is fundamental for control systems interacting with the physical world, like railway signaling or train control, where timing is everything. Languages like Lustre and SCAD, often used in these domains, also build on similar principles of synchronous execution and handling time explicitly.
Okay, so once we have these precise mathematical descriptions, these formal specifications or models, the next step is actually proving things about them. That's formal verification, right? It's not just about describing anymore, but rigorously demonstrating properties and aiming for that mathematical certainty.
Precisely. And one formal verification technique that has gained significant industrial popularity, partly due to its automation, is model checking. Given a finite state model of a system, often derived from those automata-based descriptions, and a desired property you want to check, often stated in a logical formalism like temporal logic, the model checker automatically explores all possible states and behaviors of the model to check if the property holds true.
Temporal logic, what does that let you express?
Temporal logic extends classical logic, like A and D, or not T, with operators that reason about time or sequences of states. It allows you to express properties like, it is always the case that the train doors remain closed while the train is moving, quote, safety property. Or if a request is made, it will eventually be granted, liveness property. Or it's possible to reach a state where the emergency brake is applied. Computation tree logic, CTL, and linear temporal logic, LTL, are common examples. They provide formal languages to state these complex behavioral requirements precisely. How does model checking work conceptually? Well, a simplified way to think about it is that the algorithm systematically explores the state space of the model. It might label each state with the subformulas of the property that hold true in that state, building up the verification. For finite models, this exploration can be exhaustive. The complexity is often linear with respect to the size of the model, number of states and transitions. But one of model checking's most powerful features, especially from a practical debugging perspective, is that if a property is found to be false, the model checker can often provide a counterexample.
What's a counterexample?
It's an actual execution trace, a sequence of states and transitions in the model that demonstrates exactly how the property is violated. It shows you a specific path through the system's behavior that leads to the undesired outcome. This is incredibly valuable for understanding and fixing the flaw in the model or specification.
That sounds amazing, but you mentioned finite state model. What about real software? Does it always have a finite number of states? And that state space explosion you hinted at earlier, how big a problem is that?
Both excellent points. Real software, especially when considering data values, often has a theoretically infinite or, at best, astronomically large number of states. That's a major challenge. And yes, the state space explosion problem is the main hurdle for model checking. Even if the state space is technically finite, it can grow exponentially with the number of concurrent components or variables in the system. A system with just a few dozen interacting parts could have more states than atoms in the universe, making simple, exhaustive exploration impossible.
So how do they deal with that?
Clever techniques have been developed. One major approach is symbolic model checking. Instead of representing states one by one, it represents sets of states and transitions compactly using Boolean functions, often implemented with data structures called binary decision diagrams, BDDs. This can handle much larger state spaces implicitly. Another approach is to avoid exploring the entire state space if possible. Techniques like bounded model checking, BMC, check for counterexamples only up to a certain length or depth. It translates the problem into a Boolean satisfiability SAT problem. Is there a path of length k that violates the property? Modern SAT solvers are incredibly powerful and can often find bugs quickly this way, even if they can't prove complete correctness. Other techniques involve abstraction simplifying the model while preserving the properties of interest. The availability of these advanced techniques and efficient tools like SMV, new SMV, Spin, and many others has really driven the industrial application of model checking since the 90s. Now, applying model checking directly to software source code, which we call software model checking, adds another layer of difficulty because of that state space issue and the gap between code and formal models. Pioneering work on this was done at NASA in the late 1990s, driven by the need to verify flight software. They adopted two main strategies. First, translating the source code, like C or Java, into the input language of an existing model checker, like translating C code into Promula for the spin and model checker. Second, developing specialized model checkers that directly operate on the programming language itself, like Java Pathfinder, which explores the execution paths of Java bytecode. In both cases, the absolute key is abstraction. You need techniques to extract a finite state abstract model from the potentially infinite state code. This abstraction must be sound, meaning if the property holds on the abstract model, it also holds on the real code, but simple enough to be analyzed. The development of sophisticated abstraction techniques, like predicate abstraction, has been crucial for making software model checking practical for larger systems. Java Pathfinder, for instance, has been successfully used to verify software deployed on actual space probes. Other software model checkers, like CBMC, C-bounded model checker, aim to make it easier for developers. They often come with built-in checks for common programming errors, like null pointer dereferences, array bounds violations, or division by zero, effectively hiding some of the underlying formal logic from the user. It's very likely that software model checking will gain increasing industrial acceptance in the railway domain, not just for proving core safety properties, but also for guaranteeing the correct behavior of complex non-safety related software components, helping to eliminate common bugs. Moving on slightly, there's abstract interpretation. This is a powerful form of static analysis.
Static analysis, meaning you analyze the code without actually running it, unlike testing.
Exactly. Testing is dynamic analysis. You run the code. Static analysis examines the code's text and structure to find potential problems without execution. Abstract interpretation is a specific theoretical framework for static analysis, developed by Patrick and Radia Cousteau back in the 1970s. Though industrial-strength tools supporting it, like Astray or Polyspace, now part of MATLAB, only emerged decades later as techniques matured and computing power increased. Its primary focus is usually the analysis of source code for potential runtime error detection. This means automatically detecting things like potential integer overflows or underflows, division by zero, use of uninitialized variables, dereferencing of null pointers or out-of-bounds array accesses, all those nasty things that can lead to crashes or undefined program behavior.
So it's like an automated code review looking for specific kinds of dangerous operations.
In a way, yes, but it's mathematically grounded. Since deciding correctness perfectly at the program level is undecidable, abstract interpretation works by computing a conservative and sound approximation of the program's possible states and variable values at each point in the code. Instead of tracking exact values, it might track intervals, for example, variable x is between 0 and 100 here, or other abstract properties. It essentially calculates an over-approximation of the program's behavior in this abstract domain. If the analysis shows that an error cannot occur in the abstract domain, then it provably cannot occur in the real program. That's the soundness.
That sounds incredibly useful, but if it's an approximation, an over-approximation, does that mean it might flag things that aren't actually errors? Like it might say an array access could be out of bounds, but in reality, due to other logic, it never is.
That's the trade-off, exactly. The main drawback of abstract interpretation is the potential for false positives or false alarms. Because it works on an approximation, the analysis might identify a state where an error could occur in the abstract model, even if that specific state is impossible to reach in the actual concrete execution of the program. This makes full automation tricky. These uncertain warnings or potential errors often need to be manually investigated by developers to determine if they represent real bugs or are just artifacts of the abstraction. So it's incredibly powerful for finding many potential runtime errors automatically, but often requires human judgment to filter the results. And finally, within formal verification, there's automated theorem proving. This is another approach for automatically or semi-automatically verifying system properties by proving mathematical theorems about the system model or specification. Theorem provers focus on the automation of logical deduction, how they work. Typically, the user defines the system's properties, assumptions, hypotheses, and underlying rules, axioms, in a precise formal logic language. This could be classical first-order logic, or more expressive logics like higher-order logic. The proof engine then attempts to automatically construct a formal proof, demonstrating that the desired properties logically follow from the given axioms and hypotheses. Some systems are highly automated, while others are more interactive, where the user guides the prover through complex proof steps. These are often called proof assistants.
So the output isn't just yes/no, but an actual mathematical proof.
Yes, exactly. The proofs generated describe how and why a property, a conjecture, logically follows from the initial assumptions. Ideally, this proof can be understood and checked by domain experts and developers, providing very high confidence. There are many powerful theorem prover systems available, like CUC, Isabelle HO, PVS, and ACL2. Software verification is an obvious application area. They're used for various tasks, from verifying the correctness of critical algorithms, like scheduling algorithms for fault-tolerant systems, to formally specifying and verifying requirements for key parts of safety-critical systems, including railway applications. 4. Formal methods and modeling in the railway world.
Okay, so we've talked about testing in detail and now these quite advanced formal methods. How have these highly technical, mathematically rigorous approaches actually impacted the day-to-day reality of railway engineering? Where does the theory meet the tracks?
That's the key question, isn't it? For the past 30 years or so, formal methods have indeed held this promise of being a powerful solution for the complex safety certification challenges faced by railway software designers. The railway sector's inherent drive for extremely stable technology and the relentless quest for the highest possible guarantees of safety have been key factors pushing the adoption of computer-controlled equipment, and with it, the need for rigorous verification techniques like formal methods. In fact, if you look at the EN 50128 standard again, it explicitly indicates formal methods as highly recommended for Cell 3 and Cell 4, the highest safety levels, and recommended for Cell 1 and 2 during both the software requirement specification phase and the software design phase. Furthermore, formal proof or formal verification is also highly recommended for Cell 3 and 4 during the verification phase itself, and even for verifying the correctness of configuration data preparation, which is crucial for systems like interlockings. So, formal proof and verification of safety properties are increasingly seen not just as desirable, but as a practical necessity in the railway sector, especially for the most critical functions. The tools and techniques have matured and become more common in real-world industrial applications.
You mentioned the B method earlier. Has that seen real success on the railways? It sounds incredibly rigorous.
It absolutely has. The B method has been successfully applied to numerous railway signaling systems, particularly in France where it originated. A landmark example, often cited as the first acclaimed large-scale industrial application of B, was the CC system. That's a system for driver assistance, operation, and maintenance, developed for a busy Paris RER commuter line back in 1993. Following that success, the B method was adopted for many similar systems, including the fully automatic Paris Metro Line 14. And here's a really striking finding from that Line 14 project. Several significant errors were actually found and corrected during the formal proof activities that are part of the B method, happening at the specification and refinement stages before any code was finalized.
Wow, so they found bugs just by doing the math, essentially.
Pretty much. And even more impressively, no further bugs related to those formally verified parts were detected by the extensive testing activities that followed the B development. This profound success of the B method had a major impact in the railway signaling sector. It really demonstrated the power of catching errors early through formal rigor and directly influenced the inclusion and recommendation of formal methods in the EN 50128 guidelines themselves. When it comes to model checking, its official appearance as a recommended formal verification technique in a safety-critical standard like EN 50128 came a bit later, with the revised version in 2011. Since then, model checking has become a common means to gain confidence in a design, especially for verifying the most critical logical parts of railway systems. A classic application area has been the safety verification of the logic used in railway interlocking systems, the systems that prevent trains from colliding by ensuring signals and points are set correctly. This has been an active area for model checking research and application for many years. It remains an active research area too, particularly due to the ongoing difficulty of verifying very large, complex interlocking designs. That state-space explosion problem we talked about can still be a significant challenge for the largest, most complex national-scale interlocking systems. And for abstract interpretation, as we discussed, the industrial tools supporting this form of static analysis have become more widespread more recently. Consequently, published success stories about a specific application in the railway domain are still somewhat limited, even though static analysis itself is highly recommended for SILs 1 through 4 by EN 50128 for finding runtime errors. However, there is a notable published contribution where researchers demonstrated how abstract interpretation, when used strategically in conjunction with model-based testing, allowed a major railway signaling manufacturer to reduce the overall cost of their testing activities by a remarkable 70%.
70%, that's huge. How did it achieve that?
By automatically proving the absence of certain runtime errors, like overflows or array-bound errors, in large parts of the code, it significantly reduced the number of low-level tests that needed to be manually designed and executed to check for those specific conditions. The static analysis provided the proof, reducing the dynamic testing burden. It shows the immense practical potential for cost savings alongside safety assurance.
Okay, so formal methods have clearly made inroads and shown real value. But you also mentioned that despite these successes, they have sometimes been perceived as highly specialized, maybe a bit academic, or even experimental by some practitioners on the ground. That's where a different yet still incredibly rigorous approach called model-based development or model-based design has really gained ground, perhaps offering a more intuitive path to achieving similar safety goals. It sounds like it might bridge the gap between traditional engineering and these very mathematical techniques.
That's a very accurate assessment. There are several reasons why model-based development, sometimes called MBD, often gain traction faster in industry, including railways. You hit on perception. Traditional formal methods, especially theorem proving or complex model checking, were sometimes seen as, well, rigid and difficult. Handling the tools often requires specialized mathematical or logical expertise that might be beyond the typical core competencies of many railway software engineers. Also, fully integrating traditional formal methods like B sometimes demanded a quite radical restructuring of a company's established development processes, making it harder to reuse existing code, test suites, or other artifacts from previous projects. And let's be honest, the user interfaces of many traditional formal verification tools were often designed for logic experts, not necessarily for the average engineer, lacking intuitive graphical representations or workflows. So while it took maybe 20 years or more to really consolidate the widespread use of classic formal methods in railway manufacturing, the model-based design paradigm gained ground much faster. And importantly, modeling itself has the same high degree of recommendation from EN 50128 as formal methods for specification and design. So what is model-based development? The defining principle is that the entire software development process is centered around creating graphical model abstractions of the system and its software. From these models, the actual implementation code can then be manually written or increasingly automatically generated. The objective is fundamentally the same as with formal methods: to detect design defects early, before the expensive phase of writing and debugging detailed code.
So finding errors in the blueprint rather than in the finished building.
Exactly. But MVD is often perceived as being closer to the traditional needs and workflows of developers. They often find working with graphical models and simulating them more intuitive and accessible than reasoning with abstract logical formulas or complex theorem provers. This trend has really boosted the popularity and development of sophisticated MVD tool suites. We mentioned some earlier. Tools like Magic Draw or IBM Rational Rhapsody are often used for high-level system modeling, using standard languages like UML, Unified Modeling Language, or CSML, Systems Modeling Language. Then you have tools like SCAD, Safety Critical Application Development Environment, or the MATLAB Simulating Stateflow tool suite from MathWorks. These are often focused more on detailed behavioral modeling using formalisms like block diagrams, data flow diagrams, and state charts, or state machines, which are particularly suitable for representing the complex state-based logic and control flow common in embedded systems used in railways. Typically, UML, SysML might be used for architecture and requirements, while SCAD or simulating state flow are used for the detailed design that leads to code generation.
Okay, so at its heart, MBD starts with creating these detailed digital blueprints of the system. That's the modeling part. You mentioned levels of abstraction. How important is choosing the right level?
Oh, it's absolutely crucial. Choosing the right level of abstraction for a model depends entirely on what you intend to use that model for. For example, if the model's purpose is to define the overall railway system architecture, showing how different high-level subsystems interact, like the interlocking, the train control center, the trains themselves, then using high-level languages like SysML or UML is very suitable. These focus on structure, interfaces, and high-level interactions. However, if the model's purpose is to define the precise, detailed behavior of a specific software component, and you intend to automatically generate executable code from it, then formalisms like state charts or UML state machines, or data flow languages like NSCAD are much more appropriate. They capture the detailed logic and control flow needed for implementation.
And interfaces must be key here too, how the different model parts talk to each other.
It's absolutely critical. A key step in modeling, regardless of the level, is a clear, unambiguous definition of the interfaces between systems and between software components within a system. And specifically for models that are going to be used for automatic code generation, there's a best practice. It's generally preferable to define interfaces that are composed solely of simple input and output variables or data flows, rather than complex function calls between model components.
Why is that?
It promotes better decoupling between the components. It makes them easier to test in isolation, as you don't have to create complex stubs to simulate the behavior of functions called in other components. You just need to provide the right input data values. Another absolutely critical aspect, especially when modeling for code generation in high-integrity railway systems, is the need to constrain the modeling language itself. Remember, the generated code has to strictly abide by the requirements of EN 50128, and often even stricter company internal coding guidelines. These guidelines typically forbid the use of certain C or Ada language features considered risky, like dynamic memory allocation, malloc-free, recursion, pointers, or limit their use severely, or unrestricted use of global variables.
So the modeling tool needs to prevent you from designing something that would lead to forbidden code.
Precisely. To ensure that the generated code automatically complies with these safety guidelines, the modeling language itself, or at least the subset used for code generation, has to be restricted. You model within a safe subset of the language. For example, specific safe subsets for modeling languages like stateflow have been defined and qualified for use in railway applications, ensuring the models only represent constructs that can be translated into safe, compliant code. Now, one of the main benefits, and perhaps the most intuitive advantage, of having these graphical models is the possibility of simulation. This means you can actually run or animate the models directly within the development tool. You can observe their dynamic behavior, watch how input signals affect output signals, see how the internal state of state machines changes over time.
Like a virtual test drive for the software before it's even code.
Exactly like that. In this way, the models become executable specifications. They allow engineers to observe and validate how the system is intended to behave before any code is written or deployed. You can do this by providing appropriate test harnesses or stubs that simulate the signals coming from the real environment, sensors, other systems, and observe the model's responses. This simulation feature is available in all the prominent MBD platforms we mentioned, and it's particularly powerful during the debugging phase of the design. Why? Because the modeler can often visualize graphically exactly where in the model an error occurred when a test fails. They can see the active state, the transition taken, the values of variables at that moment, the full context of execution within the model.
That sounds much easier than staring at lines of code and trying to figure out the program's state.
It often is. This contextualized visual debugging is a significant advantage over trying to debug complex logic in raw source code. It makes it much easier to pinpoint the root cause of faults found in the model during simulation or testing. And just as we test the final code, we also perform rigorous model-based testing. The testing happens at the model level. When using a model-based paradigm, the tests, functional tests, requirements-based tests, are typically designed and executed directly on the models using the simulation capabilities. Furthermore, many MBD tools offer capabilities for automatic test generation based on structural coverage criteria applied to the model itself. For state chart models, common coverage criteria include state coverage, has every state been entered, and transition coverage, has every transition between states been taken. These are conceptually equivalent to statement coverage and branch coverage for traditional code testing. Tools can automatically generate input sequences to achieve high levels of this model coverage.
So the tool helps create tests to exercise the model thoroughly.
Yes, which is very helpful. However, it's important to remember that while automatic test generation is great for achieving structural coverage of the model,
it doesn't automatically guarantee that the system complies with all its functional requirements. For this reason, functional tests, often derived manually from the requirements, are still absolutely crucial. They are defined and performed on the model, often using specialized test harnesses or stubs that generate the appropriate input signals to check specific required behaviors. And finally, the ultimate step in many MBD workflows, code generation, automatically translating the verified model directly into executable source code, like C or ADA. The code that will ultimately be compiled and deployed in the system's microprocessor is automatically generated for the validated models. The completeness of this generation varies. Some modeling tools, particularly those focused on detailed behavioral modeling like state charts or data flow, SGAD, can generate complete, ready-to-compile source code for the modeled components. Other tools, perhaps those used for higher-level architectural design, might generate skeletons for software components, like class structures or function signatures, that still require significant manual completion by the developer.
So it's not always a fully automated path from model to running system.
Not always. Even with complete code generation for the core logic, developers usually need to manually define some glue code. This is often an adapter module needed to connect the generated code to the specific hardware drivers, operating system interfaces, or other manually written parts of the system. Now, a really important point here is qualification. Some code generators, like the one integrated with the SCAD tool suite, are actually qualified according to safety standards like EN 50128 as a T3 tool.
What does qualification mean in this context?
It means the certification authorities have assessed the code generator itself and have high confidence that the generated code accurately and faithfully implements the behavior of the source model without introducing errors. If you use a qualified code generator, the verification effort on the generated code can potentially be reduced, as you have high trust in the translation process. However, if non-qualified code generators are used, which is often the case with general-purpose tools like MATLAB Simulink Stateflow, unless specific qualified code generators are purchased, then a crucial additional verification step is absolutely required. This is often called back-to-back testing or translation validation.
Back-to-back testing.
Yes. It means that the same tests executed on the model during model-based testing must be repeated on the automatically generated source code after it's compiled. You then need to demonstrate that two things match perfectly. First, the input-output behavior observed on a running code must exactly match the behavior observed during the model simulation for the same test inputs. Second, the structural coverage achieved on the code, e.g. statement or MCDC coverage, must match the structural coverage achieved on the model for the same test suite. This step rigorously verifies that the code generator correctly translated the model's logic and, crucially, that it didn't introduce any unintended additional behavior or errors during the translation process. This back-to-back testing has been widely and successfully applied in the railway domain when using non-qualified code generators.
Wow. Okay, today we've really taken a deep dive into the incredibly intricate world of developing safe railway software. It's far more complex than I think most people realize. We've seen how stringent standards like Senelec EN 50128 lay the absolute foundation, guiding every single step, often visualized through that V model. We explored the indispensable multi-layered role of comprehensive testing, from the smallest unit tests and boundary checks, through integration tests ensuring components work together, right up to system-wide stress tests, safety tests, and regression tests. And we even saw how the effectiveness of testing itself is rigorously evaluated using things like coverage metrics and mutation testing.
Yeah, the testing aspect alone is a huge discipline within this field.
Absolutely. Then we moved into the realm of mathematical certainty with formal methods. We got a sense of how formal specifications using languages like B or Z and modeling techniques like state charts and timed automata aim for unambiguous descriptions, and how verification techniques like model checking, abstract interpretation, and theorem try to prove correctness or find flaws automatically, tackling challenges like the state space explosion. Finally, we saw how model-based development often bridges the gap, offering more intuitive, graphical ways to design, simulate, verify through model testing, and even automatically generate code, all while maintaining those highest safety standards through qualified tools or rigorous back-to-back testing. So for you listening, maybe you're an engineering student, maybe you're just starting your career in a related field, or perhaps you're just a railway safety enthusiast. Yeah. What does all this mean? I think it means recognizing that the incredible safety record of our railway systems isn't some kind of happy accident. It's not luck. It's the direct result of relentless dedication, the application of cutting-edge, often highly complex techniques, and a deeply embedded culture of rigorous verification and validation. It's fundamentally about building trust, Trust in the systems we rely on, built line by line, algorithm by algorithm, proof by proof. These methods we've discussed aren't just theoretical curiosities locked away in academic papers. They are applied, practical engineering disciplines, absolutely essential for the modern railway landscape. They're really a testament to how the field continually innovates to balance technological advancement with an absolutely uncompromising commitment to human safety.
And if we just connect this to the bigger picture as a final thought, while we've gone deep into the specific tools and techniques, the testing, the formal methods, the modeling, it's crucial to remember that the foundation of railway safety isn't just in the code or the models or the standards. It's also deeply rooted in the human element. It relies on the critical thinking, the meticulous discipline, the systematic processes, and the unwavering commitment of the thousands of engineers who design, build, verify, and maintain these incredibly complex systems every single day. The tools are powerful, sure, but the safety mindset is paramount. And this perhaps raises an important question for the future, something for you to think about. As artificial intelligence, machine learning, and increasingly autonomous systems become more integrated into our critical infrastructure, not just railways, but everywhere, how will these established safety principles and verification techniques need to evolve? What new challenges will emerge improving the trustworthiness of these even more complex, sometimes opaque, and potentially self-learning systems? How do we ensure safety when the system's behavior might not be fully deterministic or easily specified up front?
That's a really fascinating and slightly daunting question for the future of safety engineering.
It is. There's always more to learn, always new challenges in this vital intersection of advanced software engineering and railway safety. We hope this deep dive has maybe sparked your curiosity and perhaps provided a solid foundation for your own continued exploration.